Hi, welcome to another edition of Ordinary Differential Equations. Today we are going to talk about special category of equations. They are characterized by having three properties: homogeneous, linear, and constant coefficient. Well, let's go after linear. Linear means your function that you're after and all of its derivative just show up multiplied by some known quantities. Constant coefficient simply means that all those known quantities are just numbers. There is no functionality of time in them. Homogeneous simply means that when we have all of these terms on one side, the other side is just zero as opposed to being some function of time. This category of equation turned out to be very simple to solve compared to what we have seen previously, which required quite a bit of algebra or calculus. For these cases, we have a simple recipe that applies to them across the board. Let's see how do we approach this problem. Uh, let's take the simplest of these cases, 2y prime plus 6y equal to 0. Well, we have seen this problem several times before. We have solved it by method of separation. We have solved it by method of integrating factor. Let's go see if we can solve it by just recalling some properties of functions from calculus. If I write this thing as 2y prime is equal to minus 6y and simplify that as y prime is equal to minus 3y, I'm now looking for a function that when I differentiate it, it becomes whatever it was multiplied by minus 3. So I ask myself, what function do I remember from calculus that when I differentiate it, a certain multiple shows up in front of the answer? That function, of course, is exponential of whatever this number is, minus 3 and say x. Or if I multiply this thing by any constant, still has the following property that when I differentiate it, derivative of numerator, which is minus 3, comes up in as a multiple, and we see that the derivative is minus 3 times itself. Well, that gives us the following idea, that we can search for an exponential type solution. Let's demonstrate that in the context of an example. Suppose I have 3y prime plus say 7y equal to 0. Of course, I could have solved it exactly the same way, but let's apply the idea of searching for solutions of a particular type. So I say consider function of the type exponential of mx, and then I say find m if it is possible so that this is a solution. So we are trying to see if it is possible to find solutions of this type for this equation. Well, how do we do that? It's okay. If this wants to be a solution, then the derivative of it by the chain rule is m exponential of mx. We don't know what m is, but if the solution is of this type, its derivative is this. When I put it back in the equation 3 times, so when I take it in the equation, I need 3 of this and 7 of that. So 3m exponential of mx plus 7 exponential of mx has to be 0. Well, we can factor the exponential. I'm left with 3m plus 7. This product has to be 0. Exponential is never 0. The only way this can happen is 3m plus 7 is equal to 0. From that, I get that m has to be minus 7/3. and therefore the solution that we were looking is exponential of minus this one. I just replace m by what I found, and I say the solution is this function, or this function times any constant would do as well. That's a general family of the solutions. Okay, now we can simplify this process. If I have this equation and I'm looking for solutions of this type, I can come directly to this equation. You see that it looks just like the original ODE. Solve that, and then I have my general solution. So from the ODE to an algebraic equation, solution of the algebraic equation, solution of the ODE. This is the process that can be applied across the board to all these equations, so long as it's homogeneous, linear, constant coefficient. We can apply this. Of course, there are going to be some additional details we have to watch out for, and the purpose of the lecture today is to go through all of these cases. Okay, this particular equation that we get here, sometimes called characteristic equation, sometimes called auxiliary equation. So typical name that they use for this thing, characteristic equation, or auxiliary equation, or associated equation, or something that says the equation that associates to the original ODE is of this type. Notice that the numbers are exactly the same for each prime. We get a power of m. To show this, let's go to something that we haven't done before. Let's go ahead and try the second problem that we have up there. Y double prime plus 5y prime plus 6y equal to 0. Again, this is linear because my function and its derivative are just multiplied by some known quantities. It's constant coefficient because these known quantities are just numbers. And it's homogeneous because the right-hand side is 0. So we start with the approach of trying to see if such a solution still applies here. Well, to check, I need to differentiate, which gives me a factor of m, and differentiate again by the chain rule. A factor of m comes from the exponent again. If I want to take this thing, plug it back in this equation, I need 1 of that, 5 of this, and 6 of this to be added up. So 1y double prime plus 5y prime plus 6y. 1 of this is just 1 m squared emx plus 5 m emx plus 6 m emx. Well, as before, we can always factor that exponential, and now we are left with 1 m squared plus 5 m. I made a mistake here. Sorry. Just 6. Notice that again, this equation is exactly what I had here. This leading coefficient is 1 over here. So I have, again, exponential is not 0. It never becomes 0. And the only way I can satisfy this equation is to have this quadratic equation. Well, that is going to be our auxiliary equation now. Auxiliary equation. Well, we chose our numbers so that we don't suffer all that much. We have seen this problem multiple times in high school. So you factor it and then you get two possibilities for m. It could have been -2, it could have been -3. So we have one solution which is exponential of -2x, and then we have another solution which is exponential of -3x. Those are called linearly independent solutions, meaning one of them is not just a multiple of the other one. It's an entirely different function, whatever this is. Not only each of them is a solution, any multiple of them is a solution. Not only these are solutions, but any linear combination of them is a solution. So you can write y as any multiple of exponential of -2x plus any multiple of exponential of -3x, and that is what we have as the general solution. Notice that the general solution has two constants, referring to the fact that our original equation was second order. Okay, that was rather straightforward. So we can take the equation from here, go to our auxiliary equation, the roots of the auxiliary equation, and from that we can come to our final solution. We don't need to repeat all these steps again because it's always the same set of steps, from the ODE to the auxiliary equation to the roots of it to our general solution. Now a few complications arise here, which are the complications you have seen in high school as well. The complication comes around when you're solving this auxiliary equation. This is a quadratic equation. You remember that when you solve quadratic equation in high school, there were three scenarios depending on what happens when you try to find these roots. Let's go ahead explore this in the context of equations that we have. So let me pick another example. Suppose I have y double prime plus 6y prime plus say 13y equal to 0. Again, another second order equation. It is linear because y prime, y double prime show up as multiplying known quantities, 13, 6, and this of course 1. It's constant coefficient because these known quantities are just numbers as opposed to being, let's say, sine of t or cosine of t and something like that. And it's homogeneous because this is 0. Later on we are going to see physical significance of some of this terminology we are using right now. For example, homogeneous refers to having no external forces in your system. At any rate, we learn up there that we have m to the power of how many derivatives that you have, and the coefficients of this thing are exactly the coefficient you had over there, 6m. This is just for the function itself. We just write that number. There is no m anymore, or m to the power of 0. Since you are not differentiating this thing, for m to the power of 0, you differentiate it once, m to the power of 1, differentiating twice, m to the power of 2. Okay, we have this equation. We stared at it for a while. See, it doesn't factor easily. We need to go bring big guns. Big guns, a quadratic formula or completion of squares. So let's just remember this crowning achievement of human mind from about 3,000 years ago. They did solve this thing a long time ago, and you see a formula, minus b plus or minus radical b squared minus 4ac divided by 2a. So when all else fails, we can always use that formula. In that case, here we get m minus 6 plus or minus 6 squared is 36. 4 times 1 and 32, and that is 52. Excuse me, 4 times 1 and 13 is 52, divided by twice the leading coefficient. So I get minus 6 plus or minus radical minus 16 over 2. Okay, we notice the issue here. We have negative under square root. So sometimes in high school you say this solution is not real, it doesn't exist, let's leave it out. But as if that's not the correct approach, we are going to see that all oscillatory problems lead to problems of this type. So oscillation has something to do with the square root of this negative. So we cannot brush it aside as something unreal or something. So what do we do? Here is the strategy. Separate the negative from the number. Square root of -1, we write it as I, and the other piece, if it simplifies or doesn't, either way, it's going to be 4i. So I have minus 6 plus or minus 4i divided by 2. So what was the property of I? Property of I, unit of imaginary numbers, is a number whose square is set as -1. Next, it's possible to simplify. Factor first. Factor first, I have minus 3 plus or minus 2i over 2. After factorization, we cancel, and I get minus 3 plus or minus 2i. So I have two solutions, minus 3 plus 2i and minus 3 minus I. So I can write my solution as, just like we learned here, some multiple of exponential of minus 3 plus 2i x plus some number exponential of minus 3 minus 2i of x. And I'll be done. That is my solution. Except that we have gotten ourselves into a bit of a pickle. What is the meaning of exponential of a complex number? Okay, as far as the algebra is concerned, we have gone through everything. Everything's fine, except that when we look at this thing, we kind of puzzled as to what does this whole thing mean. Okay, who comes to our rescue? Again, Mr. Euler comes to rescue, and we have a Euler formula that converts part of this to something that is going to be a bit more understandable. Euler formula typically is written in the following fashion. Exponential of I times the number is equal to cosine of that number plus I times sine of that number. So this is referred to as Euler half of the formulas of this class are named Euler formula, and so you get into a bit of a strange situation when we call something Euler formula. But anyway, this is perhaps the most famous one. You see it on some t-shirts and so on. Where does it come from? A little bit of explanation from Calculus 2 perhaps clarifies that, but let's put that aside for a moment so that we don't have another topic within our topic. Let's see, let's take that for granted that it is the case for an exponential and see how to convert this from the complex. So we have a complex form, complex number form. We want to convert it to something that's entirely made out of real quantity. so that we don't have the complication of dealing with complex numbers in the middle of our problem. So what do? I say, okay, I have y is equal to a exponential of minus 3 plus 2ix plus b exponential of minus 3 minus 2ix. Now remember, exponential of m plus n, you can always write it as exponential of m times exponential of n. Basic. Well, that's true for, it had nothing to do with the base e. For any base, you know, from college algebra, you add up the exponents. In reverse, you separate them and then you multiply. So here is important thing. Here's addition, and of course here is multiplication. So what I do here is that I write this thing minus 3x and 2ix and b. Of course I have to multiply my parentheses by x before I separate. Well, of course I can take my exponential of 3x and put it aside. I'll have a cosine of 2ix and b, excuse me, jump the gun, let's exponential of 2ix plus b exponential of minus 2ix. So our a and b are just any two numbers. They could be real, complex, or whatever. They're just numbers. Now we apply Euler formula. We say exponential of minus 3x. A. Euler says exponential of 2ix. Instead of theta there, let me rewrite this. Exponential of I theta was cosine of theta plus I sine of theta. So that is cosine of, my theta is 2x here. Cosine of 2x plus I sine of 2x. Same thing with b. b times, that is cosine of minus 2x plus I sine of minus 2x. Now, two simple identities from trigonometry. Cosine of a negative of one angle is just same as cosine of that angle, and sine of negative of an angle is minus sine of that angle. So what does that do? Exponential of minus 3x, a cosine of 2x plus I sine of 2x. I didn't put the parentheses, a bit of a sloping notation, but putting the parentheses makes it so crowded that you might get distracted. So we understand 2x is the input of cosine. B, cosine of minus 2x, same as cosine of 2x. Sine of minus 2x, same as minus sine of 2x. Well, now I collect my cosines and collect my sines. What does that do? Exponential of minus 3x times a and b together are coefficient of cosine of 2x. And from the first one I have ai. From the second one I have minus bi sine of 2x. Now I reason like this. A and B were some constants, perhaps real, perhaps complex, I don't know what they were. They were just constants. If you add them, well, you get some other constant. So I might call this thing constant M. Again, A and B were some constants. If you multiply by anything, including complex numbers, and do addition, subtraction, well, all you get is some constant. Let's call this guy N. Let's clean this up. Exponential of minus 3x times m cosine of 2x plus n sine of 2x. Again, I did a bit of a sloppy writing. This is really have to be in a parentheses, otherwise it could get misunderstood. Okay, uh, sometimes students wonder, well, what happened to I? Well, I is a number, just like 2, 3, or 5, or whatever. You multiply by some constants, whatever you get, if it has complex or doesn't, whatever this thing is a number. So we call it just n. So we got our solution. Now let's go rephrase the whole thing so that next time it doesn't take so much time for us. Let's see what happened. I had y double prime plus, what was it? Plus 6y prime plus 13y is equal to 0. From that, I got a auxiliary equation. Solve the auxiliary equation. I had the auxiliary equation. Let's see. So I got minus 3 plus or minus 2i. Now what happened to these things I found here? Where the real part of, this is called the real part. Real part. Here's where the real part went. And then there is an imaginary part. Imaginary part, let's call that blue. Imaginary part, aside from plus or minus, just this number. Let's just take this number. Where does that number go? Well, here is where that one goes. Okay, we don't carry the I with us. We say imaginary part is 2, not 2i. Imaginary part. Okay, so that should make the process quick, as opposed to reinventing the wheel every time we do the problem like this. Let's do another example, and this time do it quickly. Let's see. Let's also remove the so-called kid gloves. The numbers in real life are not always nice numbers. So let's suppose I have 8y prime and say 21y equal to 0. So quickly, what's the solution? You want to pause this thing, do your problem, come back and double check. So m squared plus 8m plus 21 is equal to 0. So m is equal to minus 8 plus or minus 64 minus, what is that? It's going to be 84 divided by twice the first number. So m is minus 8 plus or minus 20 or 4. Minus 8 plus or minus, right, minus 20 as minus 1 times 4 times 5. So minus 1 is I, 4 is 2, and radical 5. So plus or minus 2i radical 5 over 2. We always remember to factor first. So 2 times minus 4 plus or minus I radical 5. And then divide, otherwise you are going to forget to divide this one as well. So the short end of this thing is, these are my roots, the roots of the characteristic equation. So what's the solution? Now, instead of writing the solution in the complex form, I say, no, let's write it a real solution. Real solution means we hide, put aside, if there is any I, it's going to be hidden. So exponential of this minus 4x times a cosine of, or m cosine of, radical 5x plus sine of radical 5x, b times sine of radical 5x. So as far as application to engineering physics concerned, we say problems with oscillations. And so if you have a spring in our system and if you have some kind of damping in our system, it leads into solutions like this. These kind of systems that oscillate have a frequency or pseudo frequency. You see this number is a pseudo frequency, and they have some sort of a decaying factor or attenuation factor or something coming from your damping in your problem. Damping refers to friction or drag or something like that. That gives rise to this negative exponent here. It means your solution decays out. This type of function, you have seen them in your physics lab quite often. They are functions that oscillate, and the oscillation dies away. Old days, if you had a movie, there would be always somebody in a hospital with an oscilloscope attached to him, and you see some signal, and if the signal is flattening out, they say, well, the patient is going flat. You either have to take out your napkins and cry, or do something, maybe revive the person or something. So these are oscillations that you see from movies to your laboratory. Okay, so let's make sure we don't get lost in the detail. What we did here is we said we are looking at particular set of equations. We call them homogeneous because of the, because of these zeros on the right hand side. We call them linear because the function and its derivative just show up as multiples. Constant coefficient means we are multiplying by numbers as opposed to multiplying by functions that represent some kind of a change. So constant coefficient makes life a lot easier. We have a recipe for all of these things. We take exponential of mx as our starting guess, go ahead and find the m, come back and create our solution out of that. The main difficulty then is find the root m. So that's the problem from algebra, not from differential equation. Okay, then we said if you have a second order equation, easy case is that you have two real roots. So we call this thing two real roots. Not only they're real, but they're also different from each other, distinct real roots. And then we went to the opposite case. You say, well, what if I have two roots, but they are, so here I have two roots. Yes, I have two roots, but they're complex. I can organize them in this fashion and hide. If I want to hide, I can hide that I. One case is left out, which is, what if I have two, what's the case that's left out? Are you with me? What is left out? We have two real roots, two complex roots. What's between these two categories? The case of two identical roots, two identical roots. That turns out to be, when we have things identical in mathematics as well as in real life, time for additional complication and interesting things happening. So, like what? Suppose I have y double prime plus 6y prime plus 9y equal to 0. Okay, what did we say we do? We say we write the auxiliary equation. We try to, factor it, or whatever you do, you have one solution minus 3, and second solution is also minus 3. That's the headache. These are identical. You say, why headache? What is so big deal about having identical roots? So okay, I have one solution as before. I write exponential of minus 3x. And I have another solution. Well, pick the other guy, exponential of minus 3x. Well, that looks a little bit silly because these are same functions. They are not linearly independent. You could have collected them inside one roof, and this is just one solution. Question is, what's the second portion? So this process, what we did here is a very common mistake, to think that you just write it twice and you're all done. No. Well, case of things being identical is a headache in real life too. As like if you have kids and the kids are identical, you know, all sort of headache that you have to deal with. You cannot say I have just one kid because they look like each other. Far from it. You have to somehow manage to keep them separate from each other. Now, for sure we can know that exponential of minus 3x is a solution. So the big mystery is, what is the second solution? What is the second solution? So if you want to call solution number 1, what is it, the solution number 2? Again, that cannot be listed as solution number 2 because it's not linearly independent from the very first one. We need a linearly independent solution. Okay, how to get a y2? A whole slew of ways of doing this. In fact, we have already done this. In the previous section, we had the method of reduction of order, which was a method to get your second solution if you have your first solution. So we have that method from algebra to help us to, or the calculus we have done to help us get the second solution. Perhaps you want to try something a little bit more perhaps conceptual and less in the style of formula. In that case, maybe in your physics classes or engineering classes, you go change one of these numbers slightly. You call that perturbation. You perturb your numbers. What it does is that it split these two. They are not going to be identical. It's just move them a hair away from each other, and then you take it from there and you create your second solution. So there are a number of ways of approaching this thing, but you remember, just to be short and brief, last time we said you can have y2 in terms of y1. We had a formula that we worked quite hard for getting it, was exponential of minus integral of p of x dx over y1 squared, and again dx again. So what was this? This was, if you had a differential equation, y double prime plus p y prime plus q y equal to 0. In solution number 1, y1 is given. y1 is given. How do you get y2? That was a recipe for y2. Now I leave it for you just to apply this formula, just what we had last time. And you are going to see, for all of these cases, after you go all this process, what happens is that your y2 is simply an x multiple of the first one. Okay? we write our formula, do the integration twice. All that happens is that this all of this turns out to be just 1. Integral of that turns out to be x, and your y2 is just x times exponential of minus 3x. So what is the general solution? The general solution is going to be, your first solution was y1. Any multiple of that is fine. Your second solution is x multiple of the first, which is x exponential of minus 3x. Any multiple of that is also a solution. And one thing that we get out of linearity, and second thing we get from linearity, is any linear combination of these two solutions is a solution. So that becomes the solution that we have. Okay, let's go quickly summarize what we did here. So if I have a y double prime plus b y prime plus c y equal to 0. These are second order equations, which are the most common ones we see. We write the auxiliary equation. Auxiliary equation give us two answers, minus b plus or minus radical b squared minus 4ac divided by 2a. If b squared minus 4ac, which is sometimes referred to as discriminant of your quadratic, sometimes shown by letter delta. If this is positive, well, your roots are going to be all real. And let's, to make it simple, a, b, c are always taken to be real. And just to make sure you have a second order equation, you better keep a away from 0 so you don't divide by 0. If delta is positive, m, there's a root number 1 and a root number 2, and your solution, so whatever this formula gives you, is going to be a exponential of root number 1x plus b exponential of root number 2x. If it so happens that your b is, your delta is negative, in that case your roots are going to be two complex conjugate numbers. Let's write them as alpha plus or minus I beta. If it happens to be complex numbers of this type, then clean way of writing your answer is exponential of alpha x times a cosine of beta x plus b sine of beta x. Finally, if your delta turns out to be 0, right smack in between these two cases, you have identical roots, a number and itself being repeated. It's the same number. The root number 1, root number 2, both of them, if this radical is 0, they are both of them in minus b over 2a. Your solution will be exponential of whatever that number is times a plus bx or ax plus b, whatever. Just like we have here, if you wish to factor it, exponential of minus 3x, I have a plus bx. So the root that is repeating times the polynomial. So that covers all of these cases. Every now and then you come across the situations where some of these numbers are 0. Let me just cover that separately, even though it's just contained in these problems. Suppose I have y double prime plus 4y is equal to 0. What's special here? The middle term disappeared. There's no middle term. It's a very important example that shows up in your physics and lab classes. Refers to simple harmonic motion. The simplest form of oscillations are of this type. And what happens? Your characteristic equation or your auxiliary equation m squared plus 4 equal to 0. Okay, I hope everybody knows how to solve that. This becomes m squared is equal to minus 4, so m is plus or minus square root of minus 4. If you write that, this is 2 or minus 2, you are missing the problem altogether. This is plus or minus 2i. If you want to write it more extensively, 0 plus or minus 2i. So what did we say we do? This is my alpha, this is my beta. Exponential of 0 is just 1. And I have a cosine of 2x, so y becomes a cosine of 2x plus b sine of 2x. So this is sometimes referred to as simple harmonic motion, sometimes referred to as pure oscillation. What do you mean pure oscillation? Pure oscillation refers to this term being 0. That is a term that refers to the drag component of your system. If there is no drag, friction in your system, and you get that term becomes 0, you get pure oscillation. It's the simplest type of problem of this. Okay, similar problem is, say, y double prime minus 4y is equal to 0. Equation for that is m squared minus 4 equal to 0. This one, we don't have a headache of complex numbers, just plus or minus 2. Okay, common mistake to think the only root here is 2, but plus or minus 2. So that's like the first example we had here. So you can write your solution as a exponential of 2x plus b exponential of minus 2x. So that doesn't sound like much of a news there, except there are two functions in calculus 1 you come across that sometimes are injected into these, and they are referred to as cosine hyperbolic of x, or cosh of x is exponential of x plus exponential of minus x over 2, and similarly sine hyperbolic of x, that's exponential of x minus exponential of minus x over 2. Cosine hyperbolic of x is a very famous curve, shows up in many examples. In architecture, in design of smokestacks, in many places you see cosine hyperbolic. Sine hyperbolic rarely shows up. As a matter of little information, cosine hyperbolic looks kind of like this. Sine hyperbolic looks something like that. Okay, what's so significant about that? You can write exponential of x. If I add these two, exponential of x becomes cosine hyperbolic of x plus sine hyperbolic of x, and exponential of minus x, if I subtract these two, I get cosine hyperbolic of x minus sine hyperbolic of x. What this means is that we can go from the language of exponentials to the language of sine and cosine hyperbolic. You can go back and forth between the two of them. And if I take this exponential, instead replace it by this combination and that one by the other combination, I will get some different constants. So let's call it C perhaps, cosine hyperbolic of 2x, and say D sine hyperbolic of 2x. So that's a possibility to write your answer in that style if that is your interest. So some of these problems come up with initial value designation. So in classification of differential equations, we have something called initial. If you remember, we talked about this at the beginning, initial value problems. Like when you start a physical process, you have a certain initial value. Like if you have a ball in your hand and you want to throw it, you make a decision at what point to throw it, at what angle to throw it, at what speed to throw it, and those things are initial values of your problem. The situation at the very beginning, whatever it was, that's the initial value. So if you have a differential equation, you can have initial values attached to it. This is sometimes abbreviated to as IVP. So if I have my equation, let's write an equation like the one we started with, is one. A differential equation has as many IVPs as you have derivatives in it. So for example, you can have y and y primes designated. They are typically designated at time 0, referring to the beginning, but it can be designated at any time, y0, for example, some number, say 1 or 2, and y prime 0 will be some number 3. What that means is that when you solve this thing, you remember we solved this thing as exponential of, what was it, minus 2x plus b exponential of minus 3x. If instead of x, I put 0, it has to add up to 2. So 2 has to be a times exponential of minus 2 times 0 plus b exponential of minus 3 times 0. So that's simply just a plus b. So designating y of 0 is same as designating a plus b. How about y prime? So I need to write y prime. So I have y prime. I apply the chain rule to differentiate, minus 2 exponential of minus 2x, minus 3b exponential of minus 3x. So y prime of 0, that was 3. This was y of 0. This is y prime of 0. That simplifies to minus 2a minus 3b. So I have, to summarize, here I have a plus b being 2. And here I have minus 2a minus 3b is equal to 3. So I have a system. So IVP give me a system. I go ahead and solve this system. Okay, it's a 2 by 2 system. I go ahead and solve it. And then once I solve it, well, I go back and specify what my a and b has to be. In that case, I say I have a special solution. Special, what's special about it? Special with respect to whatever my IVP was. So that's an example of initial value problem. Something close to this thing is referred to as boundary value problem. That one abbreviated as BVP. When you play ball, of course you can take a ball, run to some place and throw it at a certain speed and so on. But the more interesting situation is throw it at somebody who is going to catch it. So not only what you do at one end of this field is important, there is a second person at some other end and he has to catch the ball that you're sending. Mathematical example of this thing is to designate values at two different independent variable values. Sometimes it's referred to as a start and end or something like that. So if I had y double prime plus 6y prime plus say 5y, what was it I had there? I had to give like a 5 plus 6y equal to 0. And then I was saying y of 0 say is 3 and y and say y of 2 is 5. I make two designations, one at say my x being 0 and the other one at the different designation. So for example at 2. and I designate what that quantity is supposed to be, or some combination of this type of designation. Then we call that boundary value problem. That one can have a course entirely related to boundary value problems. They show up in physical applications quite a bit. What we are going to put it aside, you are going to see plenty of this type of problem in the next version of this course. This course is referred to as ordinary differential equations. Next level up, something called partial differential equations. Partial differential equations, the issue of boundary value problems show up there very often, and the issue will be opened up at that stage. Okay, whatever we said for second order equation can be extended to third order and fourth order equation. You see some of these in statics problems, in civil engineering, and so on. But let's keep the problem manageable to mostly second order equations. So we could continue talking about, for example, third order equation. For example, something like this. Much of the discussion will just go through, meaning you have an auxiliary equation that looks like the following. Now we are up against solving a cubic equation. Some of you, when you took your algebra classes in high school, you did solve some cubic equation. Perhaps some of you didn't. That would be a lecture all by itself. How do you solve cubic equation? In this case, this happens to be easy that you can factor it one of a number of ways. You must have seen the rational root theorem and so on, and then you get your roots. Just as before, now your solution is going to be a exponential of minus 1x plus b exponential of minus 2x plus c exponential of minus 3x, and so on. The difficulty, of course, it will be what if it doesn't factor so easily, and that will be a couple of lectures all by itself in college algebra. How do you solve a cubic equation? Cubic equations were not solved until about 16th century, even though quadratics were done about 2,000 years earlier than that. Cubics gave human race quite a bit of challenge. So I'm going to put that aside, and if it's necessary, we come back to it and solve some special cases. Until next time, good luck and God bless.